Publish.
Okay, well, thanks, Jaroslav. Thank you all for being here. Thanks for Carlos and Michael and whoever else is involved in inviting me here. It's always a pleasure coming to Natal, such a nice place to discuss physics. Okay, so we already heard yesterday a little bit why we should be interested in hybrid magnon modes. And so I'll tell a little bit of why I'm interested in hybrid magnon modes. Okay, so here's briefly what I want to tell you about. I'll first tell you what hybrid magnon modes are, although I think that seems like futile after what we heard all yesterday already. Then I'll tell you some examples where we look at hybridized magnon modes. First, where we look at magnon-photon coupling in superconducting resonators. We saw some of that already yesterday. Then I show you how we can remotely couple two magnon resonators using same ideas. I'll talk a little bit about what I think is really the main feature of magnetic systems using non-reciprocity. And then in the end, I'll tell you why my excuse for being at a quantum magnonics workshop by coupling a magnon also to a qubit. Okay, so hybrid magnon modes. So we've seen some version of this already. If you look at quantum information systems, the goal there is to use quantum states to manipulate them for data information manipulation or for sensing. And you have lots of different quantum states that you can possibly use. You can use optical states, which are really very good because they're robust at room temperature. You can use them for long distance communication reasonably well. Or you can use microwave photons, which you can do superconducting devices, for example, and manipulate them nicely on chip and do amazing things in a dilution refrigerator. And there are lots of others, atomic systems, what have you. All of them have their own advantages, disadvantages. And for a real functional system, you probably want to think of how do you combine the advantages of one, let's say the communication here, the long distance communication, with the versatility of coupling down here in some ways. And so that's what makes a hybrid quantum system where you have all these different quantum states interacting with each other in some way. And so microwave photons are nice because you can have very long coherence times, like microseconds is easily possible. You can do devices that are on chip, and you can couple in many different ways to various different excitations. And so one of the excitations that you can couple to is magnons, which might have their resonance frequency typically in the microwave range. And by using a ferromagnetic system rather than a single spin system, this allows you to get very strong coupling, easily in the hundreds of megahertz frequencies, simply because the coupling strength is given by the individual coupling strength of each spin with the electromagnetic field, and then goes as the square root of the spin density. And so if you have a ferromagnetically ordered system, you have a very high spin density, allowing you for a very strong coupling. One way how magnons then are useful is possibly for quantum transduction. We talked about this already yesterday, that you can have magnons interacting both with microwave photons, but also with visible light photons. So you can use them possibly as an intermediary between the two. But they also couple to phonons or individual spins, all examples that we saw yesterday a lot of already. What is nice of magnons, they are spin waves, right? They behave like waves. They have an amplitude and a phase, so you can do interference kind of things, and make full advantage of the wave properties. As I said, one of the nice things about microwaves is you can get some rather complicated microwave circuitry and integrate your quantum devices, your superconducting quantum devices in there. And similarly, as I will show for some examples, you can integrate your magnetic systems into this as well. But most of these things you find also with other quantum systems. But one thing that I think magnetism is uniquely well suitable for is the inherent time reversal symmetry breaking that you have that can give rise to non-reciprocity. You have this gyromagnetic dynamics, the gyroscopic dynamics of the magnetization, which allows you to do things like circulators, isolators, these kind of things. And so really in a quantum system, if you can use a magnetic microwave guide that allows you to propagate microwave photons just in one direction, you can decouple your input from the output very easily. And that's very desirable to keep noise levels down and what. And I think ultimately, if magnetism plays a role in quantum devices, it's really this where it really matters. Okay, so it's all nice and dandy. How about connecting it to real quantum type of effects where you look at single quantum excitations? Well, in order to look at a single magnon, you really have to be able to excite or detect just a single magnon. And one way how you can do this is by using a superconducting qubit, which only is a two-state system for all practical intents and purposes. And what you can do is you can take a qubit, couple it to the electric field of a microwave cavity, take a magnetic system, couple it to the magnetic field of your microwave cavity, and thereby couple the two together. You can do this in this dispersive way where the cavity is detuned from both the magnetic mode and the qubit. And lo and behold, you can get strong coupling, see this avoided level crossing. We saw some of this already yesterday. And this allows you actually to resolve magnetic excitations at a single quantum level. So it's in principle possible. I should say this experiment has been quite a bit tour de force. This schematic is much simpler than the experiment, because in order to be able to have variable magnetic fields, you still have to shield the qubit from these magnetic fields, because otherwise there's too much decoherence. So as easy as this looks, it's not at all easy, as we also figured out. In any case, so our goal is then to think about how can we integrate magnetic systems into some coplanar scalable microwave systems, something like this. So you have a superconducting resonator, a magnetic device involved to some extent. And this is pretty much kind of the first system that we looked at, where we looked at magnon-photon coupling with a superconducting resonator. This has been done already quite some time ago. Probably the very first one was Hans Hubel, who did this more than 10 years ago. Very sorry I won't hear what he has to tell next week about what he's doing these days, but I'm somewhat familiar with it. There were a lot of other people. Most of this early work was actually done in such bulk cavities. You have a bulk microwave cavity, also similar to what we heard from Rair yesterday, using yttrium iron garnet spheres involved. And so these are bulk systems, so if you want to make some complicated system, that may not be the way to go. So in what we've done a couple of years ago is we used a superconducting microwave resonator, which is essentially a microwave superconducting coplanar waveguide that is terminated here with capacitive coupling to the outside world. So the length of this wire sets essentially the wavelength of our resonator, the frequency. And in the middle of the wire, where we have the strongest currents in our superconducting microwave resonator and the largest magnetic fields, we integrated a magnetic element. So the way how we did this is we used a niobium nitride superconductor, mainly because the TC is relatively high, 14 Kelvin. What this allows also, it allows to go to relatively high frequencies, which is advantageous if you work with magnetic systems. And for the magnetic system, instead of using yttrium iron garnet, which is by many considered one of the lowest damping type of materials, we simply used permalloy because it was easier to integrate, as also was discussed already yesterday. One of the advantage of permalloy is that the magnetization is about 1 Tesla, about an order of magnitude bigger than yttrium iron garnet, which is advantageous for getting strong coupling. So let's briefly discuss how this works. So the first thing that we do is we characterize our superconducting resonator without the magnetic material on its own. So this is what you see here. We measure the absorption of the superconducting resonator, we measure actually the transmission through the superconducting resonator, but we see this resonance peak. We see a line width that's less than a megahertz, so we get a quality factor of about 7,500 at a resonance frequency of 5 gigahertz. Now, since we were also interested in using this resonator in a magnetic field, we looked at what happens once we apply magnetic fields. And unfortunately, it's not completely trivial. What happens is we have some frequency dependence. The frequency shifts. And as you can see, there is some hysteresis to this frequency behavior. And essentially what happens is as you apply magnetic fields, you invariably also get vortices in the superconductor. And these superconducting vortices give rise to kinetic inductance that then changes the resonance frequency of the superconducting resonator. But the good thing is it's really reproducible. With each field sweep, we get exactly precisely the same kind of behavior, so that's good. So then the next thing is to characterize our magnetic resonator, our permalloy system. So now we have the permalloy on the superconducting resonator. What we do is we measure with very large power, which means we drive the superconductor into the normal state. So it's not really a good resonator anymore, and it becomes just like a broadband FMR strip line measurement. So what we see here is the resonance frequency as a function of applied magnetic field, and you can fit this to a Kittel equation. More importantly is by taking a line scan, you can look at the line width, and you can plot the line width as a function of frequency. You get this more or less linear behavior, and from this linear behavior you can calculate the damping, which is 10 to the minus 2, which is not great, but it's good enough for our purpose here. I mean, in YIG you can get maybe 10 to the minus 5. But if you look at the magnon relaxation rate from this damping, it's about 170 megahertz at 5 gigahertz, which is the resonator frequency that we're interested in. Okay, so now let's look at the two things together. So this is a reminder. This is an niobium nitride resonator without the permalloy. And now once we add the permalloy, we see that when the magnon modes disperse through the photon mode, we have this avoided level crossing here. And we see a clear hybridization between the magnon and the photons. So the magnons disperse almost vertically here because of this condensed frequency scale here. It's just very small Y scale in this range. Okay, so what happens is we get this coupling between the photons and the magnons that gives rise to this avoided level crossing. We can also look at the photon system on its own by being far away from this level crossing, and we can just look at the line width here. We see that the line width of our photon resonator has changed a little bit, got a little bit worse by integrating the magnetic system. You can also see that the resonance frequency shifted slightly. But what we can do now is we can really analyze what the coupling is. It's given by the RF field of the resonator coupling to the magnetization. So you see large magnetization helps with strong coupling. The way how we can analyze this is we can take the frequency as a function of a magnetic field and also the line width of the modes as a function of magnetic field. Analyze this with this formula where we have the resonance frequency of the photon, the magnon system. We have the individual loss rates for the photons and the magnons. And we measure this, And so we can pull out the coupling. And so what we get is we get a coupling that's about 150 megahertz. And if we calculate the cooperativity, which is now 150 megahertz squared over 170 for the magnon system and 2 for the photon system, you get a cooperativity about 70. So what this means is you can have about 70 coherent exchanges of energy between the two systems. So if you wanted to do some quantum manipulation, it's possible. But this and most of what I talk in my talk is all in the classical regime. It's not in the quantum regime. Okay, so now this was our starting point for getting involved with hybrid magnon systems. And so one of the things that we did is we made a more complicated system where we had two magnon resonators coupled to the same superconducting resonator. And then what we added is we added locally a small magnetic field coil that can locally change the magnetic field on one of the magnetic resonators. And so the first thing that we can do is we can apply an external magnetic field here and pass a small current through this such that the effective field on this sphere is clearly different from this sphere. And so we see individually each of these magnon resonators coupled strongly to the photon resonator, so we get the same avoided level splitting as before. But now what we also can do is we can detune the two magnetic resonators far away from the photon resonator. The photon resonator is always roughly at 3.8 here. But we can have the fields lower such that the magnetic modes live at lower frequencies, and then just change the magnetic field of one relative to the other. And what we see is we still get strong coupling between the two magnon modes, now mediated by virtual photon modes that are well away from this. And we can do this over relatively large distances. This is about 1 centimeter apart. And so again, if we analyze this and we calculate the cooperativity of this mode, we get a cooperativity about 90 here. But now we can become even more clever than that. What we can do is we can add two individual microwave antennas which are perpendicular to the superconducting resonator so that they do not couple to the superconducting resonator at all, but they only couple individually to the magnetic resonator that they're close by. And so what we can do now is we can excite one magnetic resonator with one antenna and measure the response at the other magnetic resonator independently of that. So the first thing that we can do is we can do the same experiment as before. Here again, our two magnon modes are detuned from our resonance cavity, and we just tune one magnon mode with respect to the other. We see this avoided level crossing, and it's essentially the same measurement that I showed you before, except that we are not measuring the response on the resonator, we're measuring it directly on these magnetic modes. But then we can become a little bit more clever and mix our microwave signal with pulse so that we get a microwave pulse, and so we can excite one magnon mode with a pulse, and then using time-resolved, real-time oscilloscope, just look at the response at the second magnetic resonator. And so this is what you see here. If we are right at this avoided level crossing, we see that the energy in the second resonator mode really oscillates, between strong oscillations, then it becomes small, strong. So you really see this coherent shuttling back and forth of energy between the two magnon modes. It's like what we said, yes, a Rabi-like, even if it's not really Rabi. And if you are further away from the avoided crossing, you see this oscillation is faster, which kind of makes sense because the modes are splitted further apart, and you get a shorter time period for the oscillation. You can look at the beating period And it really corresponds to the gap that we see in the other measurement. It makes sense. It all works out. You can also look at the relaxation rate, which is about 160 nanoseconds, which is also what we expect from the line width that we measured of the magnon modes itself. Okay, so this is just using one pulse and then the time resolved detection at the second one. Now we can use multiple pulses. We can take 2 pulses. And now what we see is, depending on the time difference between the pulses, we can either have constructive interference or destructive interference. Really what we see is that we maintain coherence of this coupled mode over a long time. So this all bodes well if you want to do some coherent manipulation of the magnetic modes in these kind of systems. Okay, so far we just look at this strong coupling between microwave photon resonator and magnon resonators. But now let me talk a little bit about what I think is really one of the important parts where magnetic systems may play a role, namely the non-reciprocal transduction. And so we know this already. If we have some quantum system sitting at really low temperatures, but we still want to read out what's happening in the quantum systems in the real world, where we're sitting in normal room temperature, we want to make sure that the signal only goes out and that the thermal noise from here doesn't go back. And the way how you do this is you have certain circulators or isolators in your system. And these are typically magnetic material based to allow microwave propagation in just one direction. But not only in the quantum information world, also if you want to do more conventional computing, and let's say you want to do computing with spin waves, what you want to do is you want to isolate the input from the output. You want to make sure that the information only propagates one way, not the other way. So you're interested in having non-reciprocal propagation of microwaves. Now, it turns out magnetization dynamics is really well suited for this. So you can have various mechanisms that give rise to non-reciprocities. One of which could be, for example, you're looking at a magnetostatic surface wave, Dehmann-Eschbach mode, we talked about it yesterday already, which lives on the surface of a thin film. It's determined by the electromagnetic boundary conditions at that surface, and it only propagates in one direction. So this magnetostatic surface wave mode on the top of the film moves in one direction. At the bottom of the film, it moves in the opposite direction. And so this is kind of nice. This works over a broad frequency band. You can use thin films very easily. This has been demonstrated in many ways. Now you can be a little bit more clever. You can use some multi-layer structure where interfacial interactions, just like Jarzynski-Maria interactions, or if you have a synthetic antiferromagnet, you have dipolar fields that interact in some k-dependent way. That also allows you to change dispersions so that the wavelength going one direction is very different to the other direction. So if you use a wavelength sensitive antenna, that allows you to also have non-reciprocal phenomena. Now, this also works over a broad frequency band, but since you take advantage of interfacial interactions, there may be some problem if you want thicker films. And as I said earlier, a large magnetization is good, or a large magnetic moment is good for strong coupling. So often you actually want rather thick films, that may limit the appeal of this. You can also do some more fancy kind of things, known as like non-Hermitian circuit engineering, where you really kind of think carefully about how you have the phase of the coupling of the magnon to your photon resonator. This can give you very strong non-reciprocities. So you see here this very strong peak in one direction, not in the other direction. Reversing the field gives you the opposite. The problem is This is very hard to engineer precisely. So in this particular experiment, for example, they were able to move the magnetic resonator into exactly the precise position. It's very narrow band. You see there's a very sharp peak. I don't know how you do it in a thin film system easily because of the complications of engineering it that well. So we really like this approach because it's quite well scaling. Now, you could think part of it is just that if you put an antenna on one side, that you couple more to one surface mode versus the other surface mode. That actually typically is not really what's going on. And when people did this in the past, you did see some non-reciprocity, but the non-reciprocity was actually rather small. I mean, the isolation was less than 10 dB. And what I will show you is that it was mostly because of a geometric mismatch of the antenna to the thin films that they used. Essentially, they used antennas that excited spin waves with wavelengths that are very long, and that actually doesn't work that well for non-reciprocity. So what we did is we used yttrium iron garnet thin film here, and we made antennas that are really very narrow, where our central signal line is just 100 or 200, 200 or 500 nanometers wide. The YIG film itself is also very thin, 100 and 200 nanometers thick. And as I will show you is by matching the sizes of the antenna to the thicknesses of the films, you get much stronger non-reciprocities. This one is 100 micrometers here. Here the scale, this distance is 10 micrometers. You know, the width of this signal line is 200 nanometers. All right. So yeah, this is big optical image, as is this. Well, so we use this ground kind of coplanar waveguide as an antenna, and by the periodicity of this antenna, we set the wavelength that we're going to excite. And you see, this is kind of the wavelength specificity. It's peaked at a wavelength that's just given by the dimensions of this coplanar waveguides. So the wavelength that we excite is about 4 times the width of the signal line of our coplanar waveguide. Okay, now if we excite a signal from the left and measure it on the right, we see that we can have a strong transduction of magnons from the left to the right. As we change the magnetic field that we apply, the frequency goes up, which is as expected. And if we look at the reverse, we excite on the right and measure on the left, we see essentially no magnons going there. So here, by taking just the line plot at one of these fields, you see we have an isolation that's easily 30 dB. The bandwidth is quite nice. It's 120 megahertz, so relatively broad bandwidth. And we can tune it easily. I mean, we went from 3 to 15 gigahertz. If we'd used larger fields, we could have gone to higher frequencies, not a problem. And there's really complete suppression of reverse. Now, for those of you that are really experts on this, if you look at the transmission, though, the insertion loss is completely unacceptable for anybody in the quantum field. We have some ideas how to address this, but we are not quite there yet. So this is maybe the engineering challenge to push this higher. So why does this work? Well, the reason is the following. If you look at your antenna, you have current going one way on the signal line, the opposite way in the ground lines. And so what it sets up a magnetic field with a well-defined chirality. The chirality is just given by your right-hand rule, Ørsted fields, something that you learn very early on in physics. And now, if you look at the transverse magnetization component of your spin wave, if it propagates to the right, it turns out that the transverse magnetization component rotates exactly the same way as this excitation field. So there's really strong coupling of this magnetic field to this magnetic mode. But if the mode travels in the opposite direction, then what you see here is if the in-plane magnetization component is aligned with the applied magnetic field, the out-of-plane is actually opposite to the field from the antenna. And so what happens here is that the coupling of the in-plane magnetization is exactly cancelled out by the coupling to the out-of-plane magnetization. And so the coupling amplitude is essentially this integral of the field distribution with the magnetization distribution. And if you choose now the wavelength to be the same as the thickness of the film, the in-plane and the out-of-plane contribution can completely cancel out. But if you have a thickness that's very different, that's not true anymore, and your non-reciprocity is much smaller. Okay. So with this, let me switch now to what you're really interested in, because you're here at a workshop for quantum magnonics, is how do we couple this to a real quantum system, a qubit, right? So essentially what we do is we take a qubit, we take our magnetic resonator and put it all together in the same microwave resonator, right? And what our goal is to simply use the qubit to detect the magnon states here. And what we want to do is not necessarily look at just an individual magnon, but look at multiple magnon states and really detect which magnon state we have with a fairly large dynamic range. So that's very different than some of the things that you've seen before. And so the way how we do this is we have dispersive coupling between the qubit and the resonator state. So the qubit and the resonator, the microwave resonator, are detuned from each other. Now the resonator has all kind of excited states, equal spacing here. And the magnon state also is dispersively detuned from both the resonator and the qubit. So that answers your question already. And so if we write down the Hamiltonian, we have, of course, our resonator Hamiltonian here, the magnetic resonator here. We have the qubit with the nonlinearity that allows us to just look at the two states here. And then we have all the various couplings between them. Now, for a single magnon detection, what you want is you want really large coupling of the qubit to the magnetic mode here. And the way how you do this is essentially by making sure that they are at the same resonance frequency. And so what that requires is that you have to have a variable magnetic field that allows you to tune the resonance of your magnetic system to be identical to your qubit. This turns out to be difficult and hard. So we did something easier. We looked at small coupling between the qubit and the magnetic system. And in that case, you don't need to fine-tune things very well, because you always have some coupling. Okay, so the way how we did this is we use the three-dimensional microwave cavity, because that does make it a little bit easier to separate the qubit well from our magnetic mode. And then we use local permanent magnets to generate a local magnetic field right here where the magnetic system is. But the magnetic field at the qubit is relatively small, and anyway it's permanent, the noise is very low, so the influence of the magnetic field on the coherence on the qubit is very small. Much smaller than if you had a variable electromagnet, for example. So we have this local magnetic field. Now we cannot tune the resonance of the magnetic system now anymore. It's just set by whatever magnets we use here. We do have this relatively low magnetic fields. We don't need any additional shielding. It's much easier in that way. We do have weak dispersive interactions between the qubit and the superconducting resonator, and the no, sorry, not superconductor, the microwave cavity. It's a copper cavity, and the magnetic system here. Okay, so how do we measure now the magnons? So the first thing that we do is we measure the frequency shift of the qubit under different population of the magnons mode. So we excite the magnons with a pulse with different power, but always the same frequency to excite the magnons. And then we just look at the excited state of the qubit and its population and how far it's shifted in frequency from the case when the magnons are not excited. And what we see is as we increase the magnon pore power, we see an increased dispersive shift of the qubit from that. Then we can also look at the dephasing of the qubit by doing this Ramsey kind of experiment here. And we can look at the decay rate, and we see at higher pump power for the magnons, the qubit decays much faster than at low decay rate. So that also tells us about the magnon population. And by putting the two together, we can actually calibrate how many magnons we get for our pump power. Because if you look careful at it, the frequency dependence on the magnon occupation and the decoherence, the dephasing of the qubit dependence on the magnon population is slightly different. And so from the two, we can calibrate what the number of magnons are. So here's the frequency as magnon population, the decoherence rate as number of our pump power. And so putting the two together allows us to calibrate pump power versus magnon population this way. And we can also use this then to calculate what is our sensitivity. And so we get a sensitivity that is of few magnons, less than 4 that we can resolve. But we can do this over a rather broad bandwidth up to a population that reaches up to 2,000 magnons. So this is what we simulate, this is what we actually measure. Now, if we had a better qubit than the one that we had, we could push this down maybe by like 50%. If we use our better qubit and a faster measurement approach, then we could maybe get a factor of 2. So we can go almost down to single magnon level. But what we gain by having the small coupling is that we can measure over a really broad bandwidth, a really large number of magnons. Okay. So if we adjust the dispersive interaction, if we make it stronger, we get higher sensitivity, but we get also smaller bandwidth that we can measure. Vice versa, if we make it even weaker, we can measure over a larger bandwidth, but there is this trade-off that's kind of inherent in all of this. Okay. Now this is nice. We can measure how many magnons we have in our system. Can we use this now to actually look at the dynamic properties of the magnons, like measuring the damping of the magnons? And so, yes, we can do this. What we can do is we can excite the magnons, and then we can use, again, like a Hahn echo kind of experiment to look at how the phase evolves. And essentially what happens now is, as the magnon occupation drops, the frequency of the qubit starts to increase, and so we get a different phase accumulation as a function of time. And so we see this here, how the phase evolves, and what we can see is, for example, how we go from like a very large magnon number, like 600 and then some, and how it decays over time towards 0 magnons here. And you see here's our phase distribution that we measured at these individual time steps. Okay. So from this we can measure the magnon decay. It's 34 nanoseconds. For those of you that pay attention, that is a little shorter than what we had with our Yick spheres when we had them in our superconducting resonator. It's mostly probably because our field with these permanent magnets, there's some inhomogeneity to it, so we probably have some inhomogeneous broadening that we have there. But so we can dynamically measure the magnon population here. Now, there's some limitation on how fast you can do this with this approach. So we were thinking, okay, is there a better way of doing this? Well, and so one of the things that we can do is we can now use a parametric pumping to pump our excited qubit state to the excited magnon state. And when we do this in resonance, so when we have a frequency that's half of the difference between these two states, we get now essentially a dynamically activated Purcell effect, where our qubit decoheres now much faster. And so we see this here. We change the pump frequency, and right here is where the frequency is actually half of the energy difference here. And what we see is that the qubit population decays much faster. Again, you see this here. This is measured when this parametric pumping is out of resonance. So we essentially look at the qubit decay on its own. And this is now when we are on resonance, so that there's additional decoherence due to the interaction with the magnons. And by doing this, we can again measure the magnon decay, and we get a number of 39 nanoseconds, which agrees very well with the other measurement that we had there. Okay, I'm going to make Jaroslav very happy because I'm pretty much already at the end of my talk, so we have plenty of time for discussion. I want to introduce you the team, though. So this is our quantum magnonics team at Urbana and at Argonne. At the University of Illinois, besides myself, there's Wolfgang Pfaff, who's our superconducting qubit expert. We have Andre Schleife, who does computational theory, Jimmy Zhu, who's an electron microscopist. And then at Argonne, we have Valentin Novosad and Yi Li, who do a lot of the superconducting magnet integration and many of the measurements. And so even Yi Li is standing here in the back. He's actually the main driver of all of this. So pretty much most of the things that you've seen, are due to him. So I owe him a lot. Now there's of course more than just these 6 senior people. A lot of more junior people are involved, both at Argonne, at Illinois. We had a young student, Myung Song, visiting from Korea, and Wei Zhang at North Carolina also helped us out. And we are grateful that the Department of Energy gave us money for this so far. I hope this continues, who knows. Now I have one more announcement I want to make before I get to my conclusions. Namely, if you really like to talk about magnetism in tropical places, I have something you may want to make note of. Namely, in 2 years, we'll have the International Conference on Magnetism, and it will be in San Juan, Puerto Rico. The water there will be just as warm as here. At this time of the year, the temperatures will be the same. So, if you like it here, you like it there. Even though it's the US, it's like the least US-like place you can go to at the moment. So hopefully I'll see all of you there. But with this, here's my conclusion. I first showed you with the superconducting resonators, we have strong coupling between magnon modes and microwave photons. Then we expanded this idea by using 2 magnetic resonators here that we can couple, and so we can have magnon-magnon hybridization mediated by microwave photons in the system. I showed you that by using the right design of your antennas, and you can now easily imagine these antennas becoming part of a superconducting resonator, you can have this very strong non-reciprocal coupling on a very small scale. So we are working on combining these 2 ideas essentially. And here our first attempts, or our first work of also integrating a qubit into this whole system here. This we did use a more 3D geometry rather than a coplanar one because it makes life actually easier. With that, I'd be happy to ask, to answer any questions. And if you like any of this, here's a more general review of what we're up to, if you want to see why we're doing the things we're doing. Okay, thank you very much.
So in the parts, like the first and the last, you mentioned magnon, but you mean the coupling to the kettle mode only.
That is right. So this, and this always is the Kittel mode. It's like the uniform magnetization precession. Here we actually do make use of propagating spin wave modes. So as I said yesterday, I think hybridization with propagating modes has been much less explored. And I think there's lots of interesting things that can be done there.
But your 3D cavity wouldn't allow a coupling to any other mode than the kettle.
Well, yeah, in this case not, because we have this rather long length scale of the magnetic field. I mean, you could probably design a 3D cavity also that could allow maybe a spin wave mode, but we haven't pursued that. No, for having propagating modes, these coplanar geometries are definitely much more beneficial because it's much easier to excite a small wavelength kind of mode. But there are trade-offs. By making it small, you also lose in coupling efficiency, and so this was kind of a little bit behind why the insertion losses are so high in these devices. But
okay, thanks for the talk. It was very interesting. So for the stuff at the end where you were doing this kind of pump probe measurement, where you excited the Yig sphere and then you looked at the qubit.
Yeah.
When you look at the qubit resonance frequency, it was interesting for me that the population of the excited state saturated at 0.5 without magnetic excitation, which is what I would expect for coherent Rabi oscillations, full amplitude. But then the peak went well above 0.5 for the shifted curves. So the two on the right that are shifted after excitation, the peak goes above 0.5. So if you do full amplitude Rabi oscillations, you would expect that it should just go up to 0.5, right? Do you know why that is, or is there?
You mean here?
No, on the left.
This?
Yeah. So what I understand.
No, this is not a Rabi oscillation. This is just directly looking at the spectroscopy.
No, I understand that this is the probability of the excited state of the qubit, right?
Yes.
And then the qubit spends 50% of its time up and 50% of its time down if it's executing a full amplitude Rabi oscillation.
Okay. But we're measuring after one pi pulse, so we put it into the excited state. So ideally, you should measure one.
So why is it 0.5 then on the left? It doesn't matter. It's just sort of broadened for some reason.
There's nothing specific about 0.5 here.
So
it's just reduced.
My understanding is it's just sort of purely incoherent on the left, and sort of maybe there's some coherence on the right. Okay, I see. So it should be a full inversion if it's an exact resonance. I see. So you might be narrowing the inhomogeneous broadening somehow with this pump. Okay, we can talk after.
Yeah.
I had another question, if it's okay. So you also you calibrated directly to the number of magnons.
Yes.
But to know that, you need to know the dispersive shift per magnon.
Yes. This is what I was saying. The frequency shift depends on the magnon number slightly different than the phasing rate. And so by having both measurements, you can actually X that out.
Okay.
So
and the assumption you're making in the end is the dephasing rate goes like the Bose-Einstein factor or something.
I'll have to look at exactly the details, but it's all the gory details. How we calibrate it is definitely in the article.
Okay, thank you.
I agree. Thanks for the beautiful talk. I noticed when you couple two magnons, that the strong coupling that you see the anti-crossings is highly asymmetric on the signal strength.
All right.
Is the first work on the this one is symmetric. If you go one slide backwards, I guess. Right. So the plot on the right, the anti-cross is highly asymmetric on the strength of the signal. And do you have any intuition on that?
I seem to remember understanding it at some point, but it doesn't come to me right now. Not entirely sure right now. But I see what you're saying. And yeah.
No, I really, I saw this before. I don't understand it. So it's, thanks.
Thank you very much for the talk. I have a question on this experiment, or well, on the experiment, on the time on this, where you put the two loops on the side there. You mentioned that you didn't get, or they're placed in a way that you don't get any interference from the loops that you were measuring. How do you not get crosstalk from the superconductor on the
that's relatively easy. That's just by having the antenna perpendicular to the resonator, right? So the magnetic fields of the resonator are in this direction, and the antenna is only dependent on the perpendicular direction.
But they don't contribute to any simultaneous drive from one to the other on the magnon. Because I think what we found is even if you have fields that are meant to be perpendicular, once you place the magnon in, then you do get some mediated crosstalk between two things like that.
Well, sure. When the superconducting resonator drives the magnon will then excite the antenna, right? That's what we see. We see the signal from the magnon itself, right? I mean, that's the reason why the signal goes, down to low amplitudes here. I mean, maybe there's a little bit in the middle. I'm not completely excluding that, but the signal from the magnon definitely dominates. I mean, so if you want the noise, maybe the crosstalk could be what you see at large timescales here.
Okay, thank you.
More questions?
Oh, we can have slow ones too. I think we have enough time.
So I was just wondering about what is the coupling mechanism that you considered between the qubits and the magnons?
Oh, the qubit is coupled to the electric field of our microwave resonator, and the magnon is coupled to the magnetic field of the resonator. So if you look at our microwave resonator cavity, so this is really how it looks like. So we have this capacitive things here where we have these electric fields to the outside shield of the cavity. And right here is where then most of the current flows by and generates the magnetic field.
Right, but in terms of like the Hamiltonian, I think I remember you writing M dagger M, C dagger C.
Yeah? So this is the Hamiltonian of the microwave resonator. This is the one of the microwave resonator. This is the qubit, and these are the coupling terms between them.
Gotcha. So it's all through the cavity. The coupling between qubits.
Yeah, so the coupling here is mediated by the cavity.
Okay, awesome. Thank you.
Okay, first you and then Carlos.
Actually, I have a related question. How do you experimentally control the coupling? You said that the coupling is small, that you're not going to the strong coupling regime.
We don't. That's the beauty here. We get a qubit that has its own resonance. Invariably, the resonance is not the same as the resonator. And the magnetic resonance is just given by the magnetic field that we have. And so we really don't do any fine-tuning. We just get them roughly into similar regions.
Thanks.
So I guess it's related to this last question. So you're measuring something here. I wonder whether you can actually use this. I mean, whether it's strong or weak. Is it the weak measurement on the qubit? What happens to the qubit when you do this measurement? Do you have to reset your qubit afterwards? I'm thinking about the usual quantum criteria. You have to initialize your qubit, then you do processing, and eventually you want to find out what the state is to continue process. So is it a projective measurement in the sense that you destroy things, or can it be controlled in a way that it's weak enough that you measure some part of the system and the qubit's still sort of intact?
Yeah, sure. I mean, we always start at the ground state here, and then with the magnon population, we look at how do we have to detune the pi shift to get to the excited state, right? So that gives us how much the qubit frequency drifts the excited one.
But is the initial state gone? Because usually dispersive measurements are such that it's non-demolition in this whatever sense that they use this word for. So the qubit is sort of not destroyed once you measure the cavity.
So what we measure the population with is with the dispersive shift of the cavity. So yes, the excited state, I guess, in principle should still be there, is my understanding.
So if
I'm not the qubit expert, so that would be better question for Wolfgang, I think.
All right.
But
okay, thank you.
More questions?
Thank you for the talk. I was interested in the non-reciprocity experiments.
Okay.
And I was wondering if you have considered using or measuring topological magnons, because these are only flowing one direction for some edge states. Do you think that would be something that you can measure with these antennas?
Measure what type of magnons? Sorry, I didn't
So
hear.
topological magnons, just as in the,
Sure. I mean, so the long-term goal certainly is, if we can use an approach like this for coupling two qubits non-reciprocally, then you can start thinking of implementing like topological codes and interactions between the quantum systems, right? So that would be super duper interesting. I mean, that's what we really hope to get to eventually.
Okay, thank you.
Okay, I think that's time to go to the coffee break, so let's thank Axel.
Thank you.